Topic of this lecture is strain. Now let's remember what we talked about last time for stress. What's the definition of stress? Well, it's just a force per area that's in the material. So since we're talking about solids, it's not really a pressure, it's a force per area over some or in some arbitrary cross-section. Now, often the cross-section is drawn perpendicular to the main axis of the member. Now, unlike pressure, well, actually pressure can have negative values too in liquids. But stress can have positive or negative values. Basically, positive values are tension and negative values are compression. Now, that's a little bit different than regular pressure because regular pressure is usually compressive, of course, and so that's what we're calling a negative stress instead of positive, whereas pressure would be positive in that case. Now, there was direct normal stress and direct shear stress. Now, direct normal stress and direct shear stress were two different types that we talked about last time. Direct normal stress is stress that comes out of the surface. It's normal to the cut surface that we imagine, whereas direct shear stress is stress that is oriented along the surface itself. Now, they're called direct stresses because they are uniform along throughout the whole cross-sectional area. Now, our topic for this lecture is strain. And let's start off with linear strain. So strain is just a way that we quantify deformation of a member that's under load. So if you think about strain, you probably prefer to think about stretching. Okay, that's probably what you prefer. And if you think about a rubber band, I'll use this example quite a bit. If you take a rubber band and you pull it, you're straining it or you're stretching it. Well, all materials stretch as a result of load. Now, how do we quantify the amount that they stretch? Well, we need to measure how far they stretch. Now, one way you could do it is with just length, but that's not particularly convenient. What's better is to figure out how much they stretch by comparison to their original length. So strain is defined as the total deformation over the original length. Now, one thing that's really important here, one of the problems is students like to think of this as the length after stretching over the length before stretching, and that's not the way it is. It's the deformation, which is usually a very small thing. So in my block here, you see block B, and you see that it's stretched. Well, that lighter section, that length that it's been stretched, is smaller than the original length. And so strain is a number that's always less than 1, okay? Unless, of course, you've strained it so much. I shouldn't say it's always. It starts off less than 1. It can go more than 1, especially in the case of a rubber band. If I have a rubber band that's 1 inch long and I strain it such that it is now 3 inches long, well, then the deformation is 2 inches over the original length of 1, and so strain can go to something like 2. But most of the time we're talking about metals and rocks and things that are very, very stiff and don't stretch a lot under load, at least not the loads we apply them to. And if we try to get them to strain a whole lot, they just fracture. So note that usually strain is going to be less than 1 for most of the engineering materials we talk about, but if it's rubber or plastic or something, you can have very high values of strain. Now notice the units of strain. It's dimensionless, isn't it? Because we have length over length. Even though it's a deformation, it's still measured in the same units as the original length. And so our units are, non-dimensional. Another practical application of strain, if you've ever thought about a mine shaft, mine shafts usually extend far into the ground, and here's a level number 27. It's 2,341 feet below the surface. Imagine a cable that has to lower an elevator of workers or maybe material, bringing up material, whatever it is. A cable that's that long, well, 2,341 feet. A mile is only 5,280. So we're approaching a half of a mile. Imagine a cable a half a mile in length. Do you think it would stretch under load? Absolutely. Even though it's wire or steel rope, basically made of steel wire, it is absolutely going to stretch. And so an easy way to think about strain is think of the unloaded length of the wire and then the deflection due to the force once you've got a lot of metal wire played out. Okay, the strain then would be that deflection delta divided by the original unloaded length. Now, if you think about what happens when you stretch material, most materials are pretty much uncompressible. Now, what do I mean when I say uncompressible? Well, you can say, well, wait a second, don't they stretch? I thought you just said they stretched. Well, there's a difference between stretching or straining and being incompressible or being compressible. Compressibility has to do with how much the volume of something changes, okay? Not so much that its dimensions change, okay? So if you think about, maybe you've used a dog bone in a class before where you were testing material samples. When you take that dog bone and you stretch it, it gets longer in length, but that material has to come from somewhere. In other words, the volume that whole sample takes up remains pretty much constant. It turns out with some metals and things it actually goes down a little bit, but that's not terribly important right now. So what happens is, as you stretch it and it gets longer this way, it gets more narrow in the lateral directions. And in fact, not only not one lateral, but both front and back and left-right laterals go down. And so Poisson's ratio is actually lateral strain over axial strain. Now, so it's not, side to side versus front to back. It's one of the strains, the one in the denominator, is the length strain. Okay, that's always the case. The change, or not just the deformation, but the strain in the direction of the load. So that's Poisson's ratio. That's the definition of it. Now, because the lateral strain is negative and the axial strain is positive, you need a negative sign in the equation. But that's just pointing out that we want the absolute value, essentially. Now, if you had a material that when you stretched it this way, it also stretched in the other direction, well, then that would be a negative Poisson's ratio material. But I don't know of any like that, because that would mean that the volume's getting larger, most likely. So here's another couple of pictures I included where we could hopefully put a little more meat around the bone. So axial strain will be our first equation. So we've got a little piece of material that has some initial shape there. We've applied a force F along its axis to stretch it out a little bit. So it's gone from an initial length LO to a final length LF because it's still under load. And so to calculate the axial strain, we need the deformation, but the deformation is the difference between the current free length and the original length, right? So that's why we have LF minus LO, in order to get just the deflection or the deformation. And then we have to divide that by the original length LO, and that is the axial strain. And that symbol, epsilon A, is what we use for our strain. The A is for axial, and epsilon is our strain symbol. Now, for lateral strain, in other words, the box that we've stretched this way is going to decrease on its side and top to bottom, right? Its dimensions are going to shrink a little bit. Let's just look at the height. So the lateral strain on the height would be just the amount of deformation on the height divided by the initial height. Now, understand that the final height actually is less than the initial, right? So technically the lateral strain we get from this equation will be a negative thing, okay? So HF is less than HO, and that difference, of course, is the deflection in the height dimension, and then HO is the initial height. So taking that difference in the ratio, we get a negative value for our lateral strain. That's why in Poisson's ratio, the final equation there, we need negative of the lateral strain divided by the axial strain, and that's Poisson's ratio. Now, in theory, Poisson's ratio can vary between 0 and 0.5, and I shouldn't have n here. The symbol we usually use is a, what is it called? I think it's technically a nu. It looks like a V. It's a Greek symbol. I'll change the slides and re-upload them so that you can see it. But that's the standard. N is not the standard symbol. It looks like a lowercase v, but it's really not. Okay, and I forgot to make that change. A half corresponds to a substance that is perfectly incompressible. So an incompressible solid. As a matter of fact, let's jump forward. Rubber actually is more incompressible than steel. Now that may surprise you a little bit because you know that rubber is actually very flexible. But what we're saying here is not that rubber won't flex. We're saying that rubber doesn't change its volume as much as steel does when you stretch the steel. And in fact, most metals have a Poisson's ratio between about 1/4 and about 0.35. Steel itself is at about 30%, 0.3. Concrete varies anywhere from about 10% to 25%, or 0.1 to 0.25. There's some Poisson's ratio values for various metals in the table over there. And I believe it's in your book as well, so you should, but I don't have a page number for you, but go look for it. It should be in chapter 2. Now, we can strain things linearly, right? We can take something and stretch it, but you can also strain things in a shearing fashion. So imagine my calculator here, okay? It's a calculator. If I were strong enough, I could apply a force to the top of this and a force to the bottom in the opposite direction and actually make the whole thing wobble, right? The sides would have to rotate a little bit. And of course, the less stiffness there is in that direction, the more I could strain it. Now, that's a different kind of strain. I'm not taking the calculator and just stretching it, right? Rather, I am changing something. I'm shearing it. Okay, it's a shear because I've got a force at the top in one direction, a force in the bottom in the other direction. So I'm applying a shearing strain to it, or I'm causing it to shear. Now, the way that you would analyze this, if you think about those elements we talked about, really on a very small element, you're talking about having a shearing stress. So before, when we talked about linear strain, we were just talking about having a normal stress, right? Something that's pulling apart. But if we have a shearing stress instead, shearing stresses tend to cause an element to deform a little bit. Not a lot. In the real world, typically the angle gamma that you see there is actually very, very small. So small it's very difficult to measure. It is measured in radians because it is an angular thing. But remember that we end up with in order to maintain equilibrium on this element, we end up with 4 stresses around the perimeter of the element. Okay, so those 4 stresses, if you look at them, it makes sense that they would cause the element to not just stretch in one direction, but to literally deform and go from a square to I guess it's called a parallelogram, right? Because the top and bottom are parallel and the sides are parallel, but we don't have 90-degree angles at the corners anymore. So that's shearing strain, and it's defined as gamma. Okay, that's how we measure the amount of shearing strain. And understand that the strain we were talking about before, epsilon, is always caused by normal stress, but the shearing strain is always caused by shear stress. Okay. Now let's go back for a minute and let's talk about linear stress and strain, so stretching something. In that case, we can define something called the modulus of elasticity, because one of the core concepts you need to get from this course is that we're interested in the force deflection relationship of everything. So if we use the ultimate tensile machines, what are we doing there? We're applying a force to a sample, pulling it apart, and monitoring the deflection, the response of it. Okay, that's really what we're interested in. Yes, we're interested in the amount of stress and strain, both, where material fails, but we're also very interested in the relationship between the stretching or the straining and the stress that's required to make it strain, or how much a strain there is at a given stress. They go hand in hand, and they're more a property of the material and the past experience of that material, but that's another story. We'll get into that a little bit later. So if we take the ratio of the normal stress, remember we're talking about normal stress, so just pulling on something again. If we take the normal stress and divide it by the normal strain, then we've got something that we call the elastic modulus. Now, the elastic modulus is usually measured only at very small strains. You could define an elastic modulus at any point, any level of stress or strain that you wanted, but it's usually taken at just the very beginning, where it turns out the two of these are linearly related. The stress and strain are a constant linear relation. One is a percentage of the other, or you could just take a multiplier. And really that multiplier is the elastic modulus, or the modulus of elasticity. Now be careful about the units here. Stress has units of, say, PSI, pounds per square inch, or gigapascals, megapascals, pascals, whatever you like. Force per area, basically. And notice that strain is dimensionless, and so the elastic modulus always has units of, well, the same units as pressure has, although really technically it's a related but different dimension, because we're talking about it in a solid, not in a liquid or a gas. Now, one thing about the relationship between stress and strain, it can be different in tension than is in compression. Now, most of the materials we deal with in this class, they'll be the same. Steel, it's the same. Okay, concrete, it's the same, but concrete will fracture differently in tension than it does in compression. As a matter of fact, concrete is a brittle material, and most brittle materials will fracture in tension much easier than in compression. But we'll get to that a little bit later. Now, really, this elastic modulus is a measure of the stiffness of the material. If you take a rubber band, for example, okay, and you take it and you strain it, okay, you could strain it where it's, now 5 times its original length, assuming it's relatively new and doesn't snap on you, right? You can strain it to where it's 5 times its original length, and you won't really have to pull real hard to do it. It's not like you have to be Hercules to pull it that hard. And good luck taking a piece of rebar and doing that to it, right? There's no way, because that much strain represents a very large difference in force requirement to get it to that position. And so you can think of it as a spring with a very low spring constant, whereas most of the time the elastic modulus is relatively high for things like steel or metals. And so it's like a spring with a very high spring constant. It takes a whole lot of force for a little bit of deflection. Okay, so it's a measure of the stiffness, just like a spring constant is the measure of the stiffness of a spring. All right. Another name for the elastic modulus is Young's modulus. So if you hear me say elastic modulus, modulus of elasticity, or Young's modulus, those are the same thing. I'll use them interchangeably and won't think twice about it. Okay. So if you think about stiffness, what does that mean? Well, that means if we use a different material, we will get a different stiffness. So let's say we make a beam out of steel. Okay, we hang a 10-pound weight on the end of it, and we note that we get a deflection of 1 inch. Now, let's say we make that same beam out of a material that is not as stiff, that has a lower Young's modulus, like aluminum. Aluminum's elastic modulus is about 1/3 that of steel's. You see it there, 10 times 10 to the 6 psi. It turns out the aluminum will deflect about 3 times as much, 3 inches there. What if we make it out of polystyrene, which is a plastic? Well, plastics have very low Young's modulus, or moduli, I guess I should say, by comparison to metals, and so the beam will deflect a whole lot more. Now, the way we represent this is on a stress-strain curve. So you'll notice on the curve on the left-hand side we've got strain on the horizontal axis and we've got stress on the vertical axis. And the ratio between those two, just if it's a constant ratio, just makes a straight line. Obviously, if we have no stress on the material, there will be no strain. In other words, there will be no deflection when there's no load. So 0, 0, 0, 0 is always a point on our stress-strain diagram. And then the steeper the initial curve, the steeper the initial slope, the higher is Young modulus and the more stiff the material is. So you can compare there. You see steel at 30 times 10 to the 6th. You should commit that one to memory. Sometimes you'll hear me say 30 E6 psi or 207 gigapascals. Titanium I don't have memorized. It's interesting that it's there. Aluminum is about 1/3 that of steel, so that's about 10 E6 psi or 69 gigapascals. Magnesium is, even less stiff, and so on. So there's a lot of materials, and they have different initial slopes for stress versus strain. Now, similarly, when we're talking about a shear stress and how remember we were rotating the element, okay, so we had shear strain, there's also a relationship between the shearing stress and the shear strain that results from the shear stress. Just like we took sigma over epsilon, now we're going to take tau, the shear stress, over gamma, the shear strain. That ratio has a name, and it's called the shear modulus. We give it the symbol G, like we give Young's modulus the symbol E, okay, capital E and capital G. Now, this is very helpful when we're talking about torsional deflection. If you have a shaft, it turns out, and let's say you're putting torque on that shaft, it turns out that the load in that shaft is primarily shear. Now, in the real world, you end up with some other loads, but primarily you mainly have a shear stress in it. And so what happens is that rod or that drive shaft will strain, but it strains where one end is rotating a little farther than the other one does. Okay, think of, I don't know, think of a screwdriver, right? A screwdriver that's really long and has a fairly small diameter, and you're trying to turn a screw. Well, it turns out that along the length of that shaft, it will actually twist, right? The end that's engaged with the screw might not move at all, but you can twist the handle a little bit. Okay, so now the stiffness has to do with the shear modulus, not the elastic modulus, because now we're talking about a shear stress. However, it turns out that there is actually a relationship between the shear modulus and well, I'll call it Young's modulus, the elastic modulus. Okay, the elastic modulus can be, or the shear modulus can be calculated from the elastic modulus, and vice versa, as long as you know Poisson's ratio. Now that's the right symbol for Poisson's ratio. That V, I think it's actually called nu. It's actually a Greek symbol. You can call it V if you want, okay? That's actually the relationship between the shear modulus and the elastic modulus. Now, let's talk about experimental stress analysis. A lot of times, either the geometry of a part that's under load or the loads themselves are too complicated for us to analyze stress. So basically what I just said is everything you learn in this class you will not be able to apply. Okay, now that's not really true, but stress and strain and loads and all these things can be so complicated that there's really not a way to analyze it simply. Okay, it's just too complicated. So why are we going through all of this? Well, most of the time when you have this sort of situation where first principles and all that is too difficult to use, number one, first principles helps you understand how stress and strain actually work. As a matter of fact, one of the things you should know by now is that there are only two types of stress. There's linear stress and there's shear stress. That's it. All right? Or normal stress and shear stress. There's no others. All stresses break down into those two categories. And I'll show you why a little bit later with stress elements, why that is, and it'll make more sense. But all stress comes down to those two. And it turns out there are combinations of those that we're interested in. But fundamentally, those are the two types of stress we have to deal with. And that's good to know when you have a part that's very complicated. But probably your go-to tool for complicated geometry will be finite element analysis. Now there are others. You can use photoelastic stress analysis. I'll show you some slides on that in a minute. And you can use strain gauges for measuring stress, well actually measuring strain at points, and using the Young's modulus you can then figure out how much stress there is. But most of the time you'll probably turn to a computer simulation and finite element analysis. It's become so common and ubiquitous, I'm sure you'll end up using it at some point in your career. Now, how are you going to know whether or not what the computer is telling you is even remotely correct, right? All it knows is what you've given it. And if you've given it something that's accidentally 2 orders of magnitude off or 100 times, out in left field, it's going to give you garbage back. So understanding kind of what results you should get is very helpful, and that's really the purpose of this course, so that number one, you can interact with finite element analysis software and do it in an intelligent way so that you can have some confidence in your results, but also so that you can just understand intuitively how these things work and how loads cause stress in even complicated geometry, so that your intuition is sharpened and your designs are better and your analyses are better and you just understand it better. That's really our goal. Photoelastic stress analysis basically just uses material that change optical properties when they're stressed. So you always have to use polarized light to see this, or a polarizing filter in order to see it, but it's really interesting. And if we were in class, you know what, we'll have some demonstrations. That's what we'll do. We'll have some demonstrations where I use what's called a polariscope and some other things to show you what these interference patterns actually look like. That's what they really are. Now we can do it with a polariscope. You can also take a photoelastic coating and put it on the part and see the same thing. But basically it just uses polarized light, and you can kind of see where stresses are highest. And in fact, on this wrench and nut, it shouldn't be a surprise to note, in fact you can tell the way this wrench is being turned. It's being turned clockwise, isn't it? How do you know? Well, notice the 2 points that are actually in contact on the nut with the wrench. You can see them. They stand out like a sore thumb, don't they? Okay, so if you don't know what that expression means, go look it up. You'll see some art and it's interesting. Anyway, you notice that there's only 2 points really in contact with the wrench, and so there's very high contact stress there, and that's where the stress is highest in the wrench. That's where the stress is going to be highest in the nut as well. Okay, so it's easy with this to very quickly determine where's the highest stress, and then also it turns out you can actually not just qualitatively but also quantitatively get a good idea of how much stress there is in various areas. But that's a little bit beyond what we're doing in this course. Strain gauges are things you've probably dealt with by now. You basically glue these little sensors to the part and then stress the part and see what happens. You put loads on it. And now these strain gauges are only good for essentially a point or a very small area. And the way they work, they're variable resistors. When you pull on them, their resistance increases. And so you use what's called a Wheatstone bridge in order to, it's just a resistance bridge and some instrumentation, in order to measure the strain at a point. Through Young's modulus then, since stress and strain are linearly related, at least if you're not really loading the material too much, then you can figure out what the stress is. Now if you get outside of the region where the stress and strain are linearly related, well then all bets are off on your stress-strain relationship. Okay. Let's see. That's it for that one. So finite element analysis is something you've heard me talk about. It's a computation technique that basically breaks a body down into a lot of really small parts, basically assumes there are springs between them, and then calculates, given a load at one point, how much stress, how much each spring would stretch. And then what's nice about it is it actually gives you the stress at every point within the model. Now, a lot of times, the finer the what's called the mesh, or the more elements you use, the more accurate results you get, but also the longer the computation time takes. Another thing, you have to choose your stress elements wisely. There are actually different types, and if you decide you want to use finite elements, I highly suggest you take a finite element analysis course. If you get the chance, take Professor Dew's course before you get out of here. It's a great follow-on to this course.